Welcome everyone to the first of a two-part webinar series on the theme of non-contact vibration, measurement and visualization. This is hosted by the Engineering Integrity Society, or EIS for short. My name is Dave Fish and I'm the chairman of the Sound and Vibration Product Perception Group at the EIS. Before we begin with the technical presentations, I'd like to just take a few moments to tell you about the EIS and its aims and role. The EIS is a charitable organisation whose primary objective is to provide a unique forum for industrial engineers to exchange ideas and experience. It was founded in 1985 and has made an important contribution to engineering science, holding major national and international conferences, organising and coordinating special task groups and presenting technical seminars. The Engineering Integrity Society consists of 4 groups: Simulation, Test and Measurement Group, Durability and Fatigue Group, Sound, Vibration and Product Perception Group, and the Young Engineers Forum. And as you can see from the list of corporate members, that we have a large number of corporate members who actively support the aims and activities of the EIS. So just before we start with the presentations, just to highlight a few up-and-coming webinars and seminars. We obviously have the second of this series of the non-contact vibration measurement and visualization webinar on the 22nd of November, which I think is a week on Monday, or which is it, Sarah?
Yeah, I'm just checking. I think it's a week on. It's a week on Tuesday.
Week on Tuesday, and that will be a presentation by Simone Manzato from Siemens on optical full field vibration measurement with digital image correlation. We also have another couple of webinars on in November and December. One on reducing doubt in engineering measurement and analysis, and then one from the Young Engineers Forum, which is how to crash an efficient lightweight structure thousands of times and survive, on the 1st of December. In the coming next year or two, we have a number of events coming up. We have in April next year, we have the Net Zero Vehicle Engineering Design and Development Technologies seminar, which is going to be held at the Institute of Advanced Automotive Propulsion Systems. And that's currently at the stage of a call for papers. So if you're interested in contributing or attending that, then please contact the EIS. We also have our annual exhibition on instrumentation analysis and testing in May at Silverstone. And then we have in 2024 the regular fatigue conference, which runs in the June of 2024 at Cambridge University. So now I'd like to finally introduce the webinar series on non-contact vibration measurement and visualization. Of course, there are huge benefits in being able to assess the dynamics of structures through non-contact methods. It is quick, convenient and non-invasive. It allows for the assessment of rotating, hot or large structures that would be problematic or impossible with traditional vibration sensors. With advances in digital cameras, laser hardware and increasing processing power, the non-contact vibration technologies have progressed significantly. So this two-part live webinar presents 3 very different technologies that illustrate some of the capabilities now available, providing the opportunity to discuss these with some of the experts in this field. So without further ado, I'd like to introduce Rob Wood. Rob Wood is a sales engineer for Zeiss and a member of the EIS Council. With a degree in automotive engineering from Loughborough University and with a test and measurement background, he has more than 10 years of experience in optical measurement systems. And Rob's title for his presentation is Optical 3D Metrology. Over to you, Rob.
Perfect, thanks Dave. So, Thanks for the introduction. So as I said, my name is Rob Wood and I work for Zeiss. You may know me from GOM previously. So GOM is a company that's taken over by Zeiss in 2019. But as of the 1st of October this year, everything in the UK is now under the banner of Zeiss UK. Apologies in advance there. You will see a little bit of a mix match of slides. So we're starting off with a Zeiss slide, but very soon we'll go into some GOM slides as well. But yeah, we'll come back to the Zeiss at the end as well. So initially I want to start with questions. A question we quite often get asked, that is, what kind of measuring data can digital image correlation provide for vibration analysis? And that's hopefully what we're going to answer today. Before we get there, though, we'll take a step back. Those of you that don't know what digital image correlation is, we'll introduce this. So digital image correlation is one of two techniques that our Aramis optical 3D sensor uses. You see on the right-hand side a pair of cameras with a stochastic or random pattern that's followed for the digital image correlation. We also do some point tracking as well through triangulation. I guess the best way of showing it is to start a video, because it'll show one of the systems in action for some more standard applications. So we're going to start off with a materials test, so a tensile test. You see the sensor mounted to the test machine, and then when the test machine is started, the camera system automatically starts recording. So we've got two cameras with an angle between them and just a central blue light projector providing the illumination, and then that speckle pattern you see on the surface is key. Essentially, we're splitting that speckle pattern up into very small measuring facets or small squares that we're going to track through 3D space as the measurement proceeds. This allows us, for example, to look at some flow fronts of strain through the material in the initial stages, and then ultimately look at the failure and the necking behavior up to hundreds of %. In the color plot here, we're looking at full field strain. That can be scaled up though, being optical. Two cameras, we can change the lenses, distance between the cameras, and the standoff distance, and in this case record at a higher frequency to look at, for example, a door slam test. And here we're looking at the at how the door performs in sort of an over slam situation. And we're going to come back to look at the door slam in a little bit more detail later. So yeah, everything we do typically is based on digital image processing, so we're using cameras. Therefore, that relies on, or the measurement accuracy relies on there being a contrast of information, some nice illumination, a good grey value distribution, and a good light intensity as well. And that's based on the two principles. So the first one, or the first measuring principle, is this digital image correlation that uses the speckle pattern. I talked about those facets. You can see those here in the picture. So the facet is tracked from the top image to the bottom, and you can see in simply 2D here how the facet is twisting and changing shape. So we're tracking that to create the displacement or the deformation of the sample. The other method is using these discrete circular markers that you've seen on the door slam example, and here we're looking at the contrast between the white and the black marker points and using that to pinpoint the center of the point. So this allows us for all sorts of different tests to generate essentially 3D surface coordinates, and from that we have a reference or a zero image, and then we can get 3D displacements, velocities and accelerations back to that, also vibration, which obviously we're going to talk about today, and then the surface strains such as you see in the video. The systems you've seen in the video are standard Aramis systems where we're providing all of the hardware. Typically those ones will go up to 1,000, maybe 2,000 frames per second. So good for slow speed and some levels of vibration testing. Where we need to go faster, we would typically have a camera system such as this. So again, still two cameras, but two high-speed video cameras, in this case from Photron, and there's just an additional light because you need more illumination for these sorts of measurements. Here we can take up where the standard systems stop at around 1,000 hertz, and we can go up to measurement frequencies of up to sort of 2 million frames per second, so pretty high speed. So the techniques of digital image correlation as well as vibration, which we're going to talk about today, are widely used. Many different materials, many different geometries, often standardized ISO tests as well. It can be incorporated into. So that's on the material side, and also on the testing of structures and components as well. There really are no limits to where the technology can be used. And of course, one of those areas is vibration. So today I want to run through a few different applications. The first one is harmonic excitation. So here we have a polymer component which is on a shaker table, and the RMS system is giving us the displacements that are shown here in this video. So the color is showing the magnitude, and then in the graph we've extracted data from 2 points on the surface to give this time trace on the right hand side. So the test essentially is to validate the calculated mode shapes. Very quickly there you can see the benefit is that we actually get to see how big the displacements are in millimeters. So we can extract those 2 points. We can extract the displacement in all 3 spatial directions, X, Y, Z in this instance, and then we can turn that into a frequency response curve, again in all 3 directions. And clearly here we can see a peak at around 287 Hertz, and this was also predicted in the simulation, and the amplitude here is about 1/10 of a millimeter at this frequency. And from that we can visualize the mode shape as well. Next example is an impact-based event, and this is the door slam test that we looked at briefly earlier, but this time we've applied the speckle pattern across the door itself and the window. We've actually used the marker points that you see around the edge and the chassis. That gives us our rigid body motion, so we're taking out that twist of the roll of the vehicle, and we're just looking at how the door behaves against the chassis itself. It's a really common test in the automotive industry. It's used for functionality of the sort of door lock system and the seals, and essentially it's a misuse test for the overslam. That speckle pattern that we've used and we've applied across the door just gives us a very high spatial resolution, giving us full field data points to choose from. You can see though that on the sort of left hand side we've extracted 2 points, and you can see in the time history plot there we've got those displacements in the Y direction, so in the sort of closing direction into the screen. Again, we can plot those displacements in all directions and calculate our frequency response curve and the corresponding mode shapes at the different peaks there. So starting off and working our way through the different mode shapes and the different frequencies. Okay, another application we want to look at is a rotating component. So here we see a cooling fan from a truck, and non-contact sensors are ideal for rotating objects. You see the RMS system with its blue ring lights in the background. Here we're capturing images at 1,000 frames per second, and the RMS system is able to calculate the position of the rotating cooling fan. So we see that we create components to track representing the complete component. So we've got the hub in the middle and each of the individual blades. So this would be a typical video showing the displacement. We can take that, we can take it relative to the hub as well, so we can really just start to look at how the blades are fluttering. And again, we can extract the deformation in all 3 directions, calculate the frequency response, and look at the mode shapes. And in these 2 examples here, you see an in-plane rotational deformation on the center image here, and on the right-hand image you see that out-of-plane deformation, which is really showing the wobbling of the blades. Okay, so how did we get to, well, from the start to that? So looking at the process within the RMS system, first of all you need to set up the RMS system. So we need to apply some points. So the points are typically easier to apply, better on structured parts, or maybe sensitive parts where adding additional mass would be damaging. So you can very quickly put on some of those sticker points, such as you see in the image there. The full field speckle pattern can also be applied just through spray paints. Here you get a a better accuracy, but also a higher data density as well. You then need to choose which frequency you're going to measure with the cameras. So obviously you need to go at least 2 times the maximum frequency. Typically for dynamic events, we would be recording at 10 times that frequency. With a simple harmonic excitation, such as we started off with beforehand, or in the first example, we could do some subsampling here, so we don't need to record as fast. In some situations, we can stagger that recording process to build up, assuming it's a harmonic excitation. So once we've set up the system, we need to acquire some images, and then essentially most of it is typically done post-processing. So we create this so-called point component or surface component, depending on whether we're using points or the complete speckle pattern. We can transform the measuring data into a defined coordinate system to define our X, Y, Z directions, apply any rigid body motion compensation, such as the roll of the chassis that we showed in the dorsal example, and then we can check for displacements. There's obviously lots of other analysis that can be done, such as 6-degree of freedom analysis as well. At that point, essentially we're finished at how far we take the measurement within inside our software. So at this point we would export typically a UFF file. So this would contain the signal, the geometry, mesh, surface, all of the information into this common, as the title suggests, universal file format. So this universal file format is supported by many vibrational analysis tools that I guess many of you will be using already. We've got documentation and workflow available on how to link this to Emiscope, BK Connect, and PAC and NumPy as well. Another example of what we support, or another example of the different software that's supported, is the Siemens Test Lab. So that's a nice throw forward into the webinar that's going to be a week on Tuesday on the 22nd from Siemens. So if you're interested more on the vibrational analysis side, then please register for that event. Okay, another couple of examples as well with some nice videos. So this is turbine fan blade inspection using the Aramis system. So typically this is used in aircraft maintenance, repair and overhaul, or MRO. So we're looking for cracks in these large fan blades from the jet engine. So if you have some cracks that are already initiated, then the natural frequencies of the component will change. So by doing this non-destructive test at the beginning of its life and during service, then you can identify the possible determination of cracks or maybe other internal problems or faults. The next example here is looking at a 3D metal printed part, and obviously with these sorts of materials and production processes, there's not too much widely available material and proven simulations. So here we're using the results from the Aramis to validate our ANSYS simulation for the mode shape calculations. And the final example, hopefully many people can relate to, is just a simple washing machine. So here, there's various things to consider. So during the spin cycle, the washing machine is going to generate potentially unpleasant noises or vibrations, which we don't want. So from an NVH point of view, it's very important to understand, but also from a product quality point of view as well. So we need to understand how these vibrations can impact the overall quality of the machine. So you see the two examples here with the side panel vibration and the heating vibration. Okay, hopefully you've seen many examples and benefits to optical 3D metrology for vibration analysis. To sum up, basically it is a non-contact measuring principle. In terms of setup, there's no wiring needed, such as with accelerometers, so it really is fast to set up and calibrate the sensor. We're reducing it down to minutes, where typically certainly on a large test, you could be working for days or even weeks to set up accelerometers. The markers themselves are very lightweight, so suitable for certain applications where you don't want to add mass to the structure, but they're also durable as well, so the same sensor and measurement points can be used again and again for many different tests, and clearly the amount of data that you can get is is quite large. So even with the marker points, you can stick hundreds of marker points on, and with the full field speckle pattern, you're getting thousands of points. And importantly as well, each of those points is a 3D displacement. So if we're putting one sticker down, you're getting the equivalent of a triax accelerometer. We also seen some applications of rotating components, much simpler here because obviously we've not got any wiring. Other things to consider as well around the whole test is that we can actually measure the excitation as well. We didn't see any examples of this, but if the excitation is in the field of view that the cameras can see, we can put marker points on this or to measure it, or we can bring in analog signals from the excitation source and sync that up with the measurement data that we're collecting. All of this can be done in real time as well to provide sort of real-time digital outputs of the displacement. And then finally, as we've seen in that final example, validation of FEA is another area where this can be applied, and we've got techniques for bringing FEA into the software and doing a real direct comparison. Okay, so just to wrap up a little bit, I want to introduce Zeiss. So as I say, Gallant were taken over by Zeiss in 2019. And as of the 1st of October here in the UK, we've been all Zeiss. So Zeiss is a very large company. We're talking nearly 36,000 employees worldwide. It's been around for 175 years, founded by Carl Zeiss and his business partner Ernst Abbe. And really their aspiration of cutting-edge research and extreme precision and maximum quality still exists within the foundation that they've created today. So today, it's split across into 4 main segments. I admit I didn't know some of these applications when I started with Zeiss, but the first one there, semiconductor manufacturing technology. So 80% of microchips worldwide, so from your phone to your car, are all manufactured using an AMSL lithography technique, which relies on Zeiss optics. Jumping over to the medical technology, so 300,000 surgical procedures are performed every year using a Kenevo 900 surgical microscope. So this is typically in brain surgery and those sorts of complex surgeries. And then maybe the one that most people know the brand or the name Zeiss for is in consumer markets. So here we're talking about binoculars, hunting scopes, glassware and eyewear, and also camera lenses as well. So it's within this area of the business that 50 camera lenses have been sent to space as part of the Apollo missions. And then the final one, industrial quality and research, that's where I sit and where the products that we've talked about today sit. So in that division, there's 7 different sort of business units or areas. So there's traditional multi-sensor CMMs. So these are your traditional tactile CMMs and optical-based CMMs. There's also optical systems. So this is a lot of the technology from the former GOM companies. So as well as the Aramis system that we've talked about today, there's also 3D scanning capabilities. Other areas of measurement include X-ray, so 2D and also 3D computed tomography X-ray, and also industrial microscopy solutions involving a whole wide range of microscopes, from simple light microscopes up to scanning electron microscopes and beyond. Everything obviously needs to be underpinned by software, so Zeiss is a little unique in providing normally software and hardware solutions and enabling that software or enable you to make intelligent decisions with your data. And finally, the last 2 sort of areas are solutions, so delivering a complete off-the-shelf automated solution, and also services as well, so be that contract measurement services or application on-site support. So that brings me to the end of the presentation. We'd at this point invite any questions. I don't know, have a quick look and see if there's any in the chat, or feel free to unmute yourself and ask a question directly.
Thank you, Rob.
So I don't believe there are any in the chat area.
So if anybody wants to unmute their mic and ask a question, they're very free to do so. I'll ask a question in the meantime.
Yeah, sure.
Can you just tell us a bit more about what the typical bandwidth capabilities and limitations are for different applications?
Yeah, so obviously it is limited to the speed of the cameras, but with increasing speed for cameras, then you're able to go faster and faster. So especially if you think you're wanting to measure typically 10 times your maximum frequency of interest, sort of standard systems would measure up to sort of 1,000 or 2,000 frames per second, so would be good for a frequency at up to say 100, 200 hertz. The next big jump comes in using high-speed cameras, and as I say, they go up to, well, they can go up to a couple of million frames per second. So that really does enable you to increase the sort of level of frequency that you can measure. But yeah, for a very high frequency, you're always going to struggle. And there's obviously a cost implementation of these cameras as well, and you need two of them.
Okay. We have a couple of questions. David Lincoln's asks, could you show the materials and test example slides again, please?
Possibly. Let me see. This one.
I'm not sure if there's a further question beyond that. And perhaps if there is, then in the meantime, Martin Dale says, can you explain how the shutter can be considered as a type of anti-aliasing filter?
Yeah, good question. So you've kind of explained it there. So yeah, the camera shutter, so this is how long the shutter's exposed to bring the light in. Obviously this needs to be of a certain magnitude of time. So if this is open for a shorter time, it's a way of getting rid of some of the higher frequency content possibly that will be coming through. I think David just wanted to see some pretty pictures. This quite cool slide. The smoke was included,
that's
just
great.
showing the wide range of different material tests. So although this webinar is predominantly about vibration, I guess a lot of people would be involved in other material tests. So yeah, there's quite a wide range of applications and some nice, pretty looking colour plots.
Okay. Well, thank you, Rob, for your time. And we'll obviously, if there are further questions, perhaps at the end of the webinar, then I'm sure that you'll still be here to answer those questions.
Yep, I can answer that at the end. Okay, thank you very much.
Thank you. Okay, we'll now move on to the second presentation in this first part of the series. This is from Keith Gallant from RMS Reliability. Keith's background is in vibration analysis for rotating machinery, working with manufacturers and process plants to improve reliability of rotating plant. Involved with IoT innovation projects and pioneering new applications for motion amplification, regularly supporting work on projects in a variety of industries that require vibration troubleshooting. Keith's title for his presentation is Motion Amplification of Operating Deflection Shapes in Near Real Time. Over to you, Keith.
Thanks, Dave. Hello, everyone. Thanks for joining. Let me just get my slides up. So, embarrassing company page has got my face on the front of the standard presentation. So RMS, we're a distributor of the technology for RDI technologies, which are based in the States, and the sort of key product is motion amplification, and that's what I'm here to talk to you today about. So this is relatively new as a vibration technique. In 2016 it became publicly available, and the way that we measure through the camera is a patented proprietary algorithm. There's not a lot they'll tell me about it, so as much as I can I'll share with yourselves. We can measure up to 702 hertz in HD resolution. We can keep going much higher. And again, that depends on your camera that you've got to connect to the system. We can take in with the RDI family of cameras up to 29,000 frames per second. but we can also plug in vision research cameras and photon cameras. As long as they're mono, they'll work with this system, and you can then get much higher frequencies and higher quality at those frequencies. So yeah, essentially this technology turns each pixel into a vibration sensor. So we're measuring in the pixel, within each pixel, the displacement that we can see on the object that we want to look at. So you'll see here a few videos. We like to show a normal video and then show the amplified measurements video. So you've got a normal video on the left here, and that's the same video on the right hand side. We've just taken all the measurement points and amplified them, times them by a certain factor. So we go all the way up to 500. So my background is more in rotating equipment, but I've got a nice variety of case studies here to share with you. And I've also got a bit of a live demo I can share. So the idea of this technology really just is opening our eyes up to really seeing what else is happening on the machine or on the product that you want to test, or the parts. Because each pixel, if you think in the camera we're using today is a 2.3 million pixel camera, each pixel becomes an accelerometer essentially. So where would you put that many sensors if you could? We don't need to put any patterns on the system, on the product or the object we want to look at. We just need to put the camera in front of it, get good contrast across the image, and then record, and we've got good data. So again, no contact. We don't have to go and attach anything. We don't have to put accelerometers on there. We don't have to put any speckle patterns on. As long as we've got that nice contrast, we can get good vibration measurements from anywhere on that image. So it goes from the point by point sort of visualization, looking at the spectrums, waveforms, trying to understand the mode shapes, maybe building a model. Now we can just look at it real time and fill in all those gaps. Excuse me. So I'll just quickly show you a live version of the system from my lounge. So just, can you give me a shout, Dave, if you can see my my IRSM
Yes.
screen?
I can see the screen, yep.
Okay, so now I'm just going to try and do a bit of a live demo. So this is, yeah, I'm just going to tap on the box there. We can hit amplify live, and all I've got in there is a little fan with an unbalance on it, just to give a bit of vibration, just to show how quick this system is. Bit of a delay on my update there. Let's bring that up. So again, now, yeah, and the great thing about the technology is, as it updates so quickly, we can make changes and see the response very quickly. So I'm even going to, I've just put an Aldi, my wife's special Aldi catalogue, put that on there and see how that affects it. Great stuff. So if I take that off now, I can also measure live. So I can just draw a box. We call these ROIs, regions of interest. What the camera's doing, it'll take its averages across all that box. So all the pixels within that box, I'll get an average vibration measurement from that, a waveform and a spectrum. So I can redraw that again if we want on here. Just as long as we've got the contrast, it'll get an accurate measurement. So the other thing for our accuracy, for amplitude accuracy, is just that we need to put in a distance. So the distance and the focal length, that gives an overall distance to the point of measurement. We can add multiple points. So if we've got some depth to our image, we can tell the system that this pin here is, let's say that one's 5 meters. We can add another one and say that this one is closer to us, maybe only 1 meter. And that way we can then get multiple measurement points, still maintaining that accuracy throughout the image. So really easy to set up, as you can see. Nice quick live demo. So if you've got any questions, throw them in the chat. I'll try and answer them as I'm going through this, but I'm going to start looking at some case studies now and show you some examples. So I really like this one. The non-contact aspect Dave touched on earlier is really interesting for tester measurement, because for me one thing is the observer effect. So if you've got a really lightweight product or a lightweight component that you want to measure, obviously when you add an accelerometer onto it to measure and test that product, you're adding weight and you change the dynamics of that structure. And this video just demonstrates that on such lightweight components. And we can see adding a mass brings down the frequency. Okay, yeah. So yeah, this is just a thin piece of steel. Room for its natural frequency, 5.31 Hertz. Add a small weight and immediately change that frequency by adding the mass. We bring it down the frequency range. So yeah, and a really nice like feature of this non-contact sort of vibration. So the other side of it is like we're filling in all those gaps. We're not putting sensors in specific places. We're actually just put the camera on, film the whole object, and you can see an awful lot more. And then once you identify areas that you can see there's more vibration or there's a certain mode shape you want to look at, you can then zoom in. You can change the lens, move the camera. It's very agile. You can just pick it up and move it, and then zoom into certain areas and hone in on that area. So like I say, if we wanted anywhere there, we can get a measurement, but we can improve our resolution just by moving the camera through a box. As long as we've got some contrast there, we'll get that measurement. So there's the in displacement microns, and I think here is revving the engine just to give us some excitation on it. Again, this isn't what you'd see with your eye. This is amplified. So the video side, the visual side, is amplified to aid you to understand the motion. Another feature of this technology that's really good, because it's vibration, we can add filters. So we can get raw data that looks sort of not that great to look at. We're not getting a lot of feedback from that. We can take measurements from there. Once we've got our measurements, we can filter it. So this one's at 12 Hertz bandpass, and I've called it porpoising. I don't think it's the same porpoising that's going on in F1 at the moment. Yeah, I think this is just the tire deformation, but you kind of see the point in the filtering. Now at 39 Hertz, you can see that twisting on the body. So that real simple feature from a vibration aspect is phenomenal, because I can look at a big area and say, well, all these different frequencies that I'm seeing, what's reacting at that frequency, and I can just bandpass to a certain frequency and eliminate anything else at other frequencies and see each individual part that moves at that specific bandpass that I want to see. So ping testing or impact tests to see a natural frequency. Yes, we can take a measurement from that as we do it. This is a fan inside of a fan on a polyester plant. This is where the shaft is, just here, and this is the fan blade. So inside there is the impellers vanes. So my colleague here has got his hammer to bump it, his modal hammer, not connected. Play it back, visual side of it. This is filtered to 44 Hertz, where we saw that dominating peak there in the spectrum. And this fan runs at 49 Hertz. So you can see it's very close to its natural frequency, and we're going to get these mode shapes while it's running. Another similar application, much larger machine. This is on a shaker screen that's used in a lime kiln plant, so where they have to shake the stone into the kiln. When we add the stone as mass, we take the stone away, obviously the machine's lighter, and the natural frequencies were changing. So here with the bump test, we've got 23 and 28 hertz amplified. There's not an awful lot to see. This direction's much better. You can see the lower modes there from the AV mounts. Now this is adding the mass with stone. We get change in our natural frequencies. So again, we take measurements anywhere on there. If we do want to mark it up to improve that, we can do with some paint markers or stickers. So that's the 16 hertz. We didn't see an awful lot. At 23 hertz, you can see all this twisting on the machine. That's amplified up to 250 times. And the fault on this machine, they had the shaker motors above were breaking the machine. They were flying off the shaker motors. And those motors were running at the frequency that we just identified there. Or just close to it, within 20%. So there's some other little features within the software which are really handy, which are really nice. Sorry, this is not full screen, this one. We can look at a large complex machine, lots of components, like we said there, amplify the whole lot and filter for different areas. And within the system, we can draw those ROIs and extract specific areas of spectrums for those areas. But we can also do what we call a motion map, and it's like a heat map of the highest amplitudes and different frequencies. That's this one here. So it highlights certain areas at different frequencies. You can then filter for them, look at just those frequencies. So it's a way of scanning complex areas a lot quicker by building that power spectrum we've got there. Some rotating components. We've got a new application that's really nice feature, and we call it tack sync. And what we can do is, with some tack tape on a moving rotating part, we can use a tack pulse to fire the camera. So you can just see here the line out from the tack goes into the back of the camera. And it doesn't matter which direction the camera's in, as long as we can see the area that you're interested in. We can change angles and so on. That feed will be firing the camera from the tack. Every time it sees the pulse, it'll fire the frames. So your sample rate becomes the 1x. So it becomes the speed of that shaft. So you can see mode shapes that are around the 1x, anywhere that's close to the 1x. So rather than me waffling about it, let's have a watch the video, because it is quite good. So that is a spinning fan, and we've frozen it like a strobe, but we've done that with the camera. And because we've got this measurement capability and amplification, we can amplify that, and we can measure points on them. So this one's pretty good, this fan. This is a new design, and I'm going to show you in a second the old design where they had problems on the fan, and it was causing cracks. So this is the old design. You can see immediately more movement. So by zooming in, improving resolution, you can really hone in and see how that motion is on right up close to the hub, the fan, and it starts twisting on the shoulder there. That's where the cracks were on the fan. There's one that's had strain gauges on. Okay, another new design. If I just skip along, should have some images of the damage. Yes. Yeah, okay. Sorry, I thought I had some. Oh yeah, there you go. Yeah, so you can see there the cracks on that area play into where we're seeing them. Okay. So we can also do some sort of the more traditional motion tracking with camera. We can pick a point, allow a transient event to happen, and track that event as it moves through the image. And the plus side of using motion amplification is we can also extract the vibration from that point as it moves through the image. So we get both that sort of overall displacement, but we also get any vibration displacement that's within the point as it moves. And we can also then add the amplification like you see here, and it just shows you the stresses on the machine. Again, another example of that. This has got the tracking the helicopter as it comes in. This is on a ship, so if you look to the bottom left, you can see the sea rising and falling. So we can track that displacement, grab the vibration out of it. We've got the rotor and the blade path and the tail rotor on that spectrum there in the top right. So it's not just smaller structures and things, we can do large structures. Not amazing amplification here, but just to show you that if there is movement there, we can amplify it. And we've now got much better sort of algorithms in the technology to enhance this. I could probably improve this a little bit of an oil rig. So once it gets energy from the waves, it does shake a little bit. And I think also on this one there's a helicopter that just there. On rotating plant, like I say, that's more what I'm used to. On a big pump at an oil refinery. This is a bearing that had poor machined housing, and it just shows how you can really see the forces on that machine. Really highlights it on this video. It's a nice one. So again, they had repeat failures in this bad machining. So size-wise, we can go straight down to really small sizes. This got nothing to do with this one. This one was given to me from RDI. I didn't know that our DNA moves like that under the microscope. But because our cameras that we use, the RSM, that's C-mount. A lot of microscopes are C-mount, aren't they? So you could mount this camera on a microscope if you wanted to, like this. Yeah, so that's it for my presentation. I've got time for questions there. Hopefully I didn't speed too quickly through it.
Okay, thank you, Keith. Do we have any questions? If I could ask one, you were showing images of structures with a reasonable amount of depth of field and also moving objects as well. How does the hardware deal with the focal side of things and the accuracy that might, or limitations and accuracy that might bring?
Yeah, so in terms of accuracy, it's if something's moving through our field of view, we do want it to be a consistent sort of in-plane distance. Our amplitude accuracy relies on the distance, but the frequency will always be right there as long as we sampled it correctly. The frequency will be right, so that's not too big of an issue if it's only the frequency you're interested in. And if you want accurate amplitudes, you just need to have a transient event that does stay relatively stable in the plane. Yeah.
Okay. And the other question I had, which you sort of actually answered in that DNA slide, is the displacement threshold for accurate visualization, is that limited down to the quality and the type of optical hardware you use?
Yes, yeah. So obviously it improves with better cameras, but we have quite a good minimum displacement resolution. So we can go to sub-micron very easily using something like a 50mm lens, and as we're under a meter, it should be sub-micron. The further away we go, obviously the lower resolution we have,
Yeah.
and the lower the bigger the minimum displacement number.
Okay. Well, thank you, Keith. That was very interesting, and I'd like to, unless there are any more questions, I don't think there are. I don't see any. So I'd like to thank Rob and Keith for their informative and interesting presentations. It's been really, really good. And I hope that you've all found this to be valuable for your own work and studies. And just as a reminder that the final part of this series will be held in a week on Tuesday at 1 p.m. With a presentation by Simone Mansato from Siemens on optical full-field vibration measurement with digital image correlation. Many thanks from the IS for making the time to attend this webinar, and we look forward to seeing you all again. Thank you.